Hi, I'm Todd Cook. Welcome back to the kitchen for another episode of Polymer E-Club's Ask the Cook. We're here to talk about polymers and polymer application. We help you answer the question, what do you need to know to add polymer skills to your career? Every injection mold, every mold for that matter, has some way to cool down the polymer melt so that the solidified part can be extracted from that mold. In prototype molds, there may not be a cooling system per se, but the cavity block is held at room temperature by the fact that it's a large block with a very high heat capacity, a material of metal, being used to solidify a plastic, which has a relatively low heat capacity. And they also cycle the mold quite infrequently in prototypes, and so that helps keep the mold temperature down, keep the mold temperature steady. As the sophistication of the mold increases, cooling channels are often drilled all the way through the mold and connected together by hose type jumpers, some with quick connects, fed by city water in some cases, or the coolant from a closed loop coolant system, or in extreme cases, because you need really high temperature, maybe oil, where the mold temperature that's desired is above the boiling point of water, for example. An important consideration in cooling systems is to prevent fouling. That's the corrosion layer that builds up on the inside of the cooling channels. Corrosion's a ceramic, so it's not a very good it's an insulator, right? It's not a very good conductor, so it's very difficult for the heat to get from the metal into the coolant to be carried away. So very important to prevent that. Another important aspect is how well developed the flow of the fluid is, the coolant itself. This is a process parameter that can be used called Reynolds number. Reynolds number basically defines the point at which flow becomes fully developed enough to begin to do the heat transfer in the most efficient way. It's a dimensionless number, meaning the number itself does not have units. All the units cancel out in the calculation, so you can compare Reynolds numbers no matter what units you're in. Reynolds number is calculated as d rho v over mu, so the diameter of the cooling pipe, the way to calculate the area, the density of the coolant, its velocity, and its viscosity, divided by its viscosity. So that cancels out all the units and gives you this number, the Reynolds number, which needs to be 2100 for fully developed flow. Now, there's really no such thing as more than fully developed flow, so there's really no point in spending the energy to raise the velocity above the necessary value to get the Reynolds number to 2100, no sense in wasting energy. But if you don't have fully developed flow, you're going to have problems. Now, conformal cooling systems are considered state-of-the-art, but if your conformal cooling channel is large and follows the shape of the part, for example, that can cause the Reynolds number to drop because the velocities in those larger channels go down, and so the Reynolds number goes down. And it's possible that you could have poor heat transfer performance even in a very advanced cooling system. Knowing how to use Reynolds number and other properties of your cooling system to get the most from it, that's working knowledge. Just what you'd expect when you watch us here at Polymer E-Club, Ask the Cook. Now, don't forget to subscribe, like, turn on notifications, and share if you appreciate the content. Also, you can follow a link in the description to learn more about Polymer E-Club and how to get involved. I'm Todd Cook for Polymer E-Club, Ask the Cook. Thanks for watching.